afternoon to everybody, and it's actually morning here in China. I'm going to speak a little about one of the technologies that now in academia and also in the industry in recent years. We know that in recent years there is a trend that the ships are using smart technologies like what we have on our phone, like face recognition. In the ships, one of those technologies, like the face recognition, is called the smart hull. The so-called smart hull is that we use a combination of hardware and algorithms, so that the ship knows what is going on with itself and also what is happening in the environment. And the ship is going to find out the best strategy for the operation by itself. This is a concept of smart hull. Well, it is called smart hull, but actually most of the topics in smart hull is about structures, because in addition to the structures, what we have is hydrodynamics, but not much we can do about the hydrodynamics. I will speak a little bit about the background, then I will come to the structure stress boundary, which is the foundation of smart hull, and then I will be talking about the technologies that we are using nowadays for smart hull. I'm going to start with the concept of smart ships. The concept of smart ship has been proposed with distinctive features of comprehensively utilization of technologies of sensing, communication, Internet of Things, network, to automatically acquire the operational data of the ship itself, environment, logistics, ports, aiming at improve the structural reliability, economic efficiency, environmental protection in the area of maritime navigation, management, and maintenance, and also the logistics. So why smart ship? In recent years, we probably have already had the sense that the classical mechanics, including the structural mechanics and also the marine hydrodynamics, they have already been quite well studied, and we don't have much we don't have much new technologies to improve the efficiency of the ships. I mean, we don't have much knowledge, we don't have much from the classic structural mechanics, we don't have much from the classic structural mechanics, and also including the design, maintenance, etc., to improve the safety, the efficiency, etc. And on the other hand, with the development of the hardware technology, the development of the software, the algorithms, we are able to apply those technologies in the traditional ship industry. So with the help of the hardware, the computer hardware, and also the sensing technology, and also with the algorithms, we're able to improve the safety. Because as we know that 80%, almost 80% of the ship accidents, they are human factors. So if we make the decision with the help of a smart system, or if we make the decision, or we let the ship make the decision all by itself. Sorry, I just forgot that I didn't turn on the video. All by itself. So we can reduce the possibility of the accidents. And of course, we are also going to have the benefits on the economical side. So we're going to have a better designs to reduce the weight of the ship itself, and from which we're going to reduce the oil consumption by 1 to 2%. The same thing with engine power rundown when resistance force diminish, load optimization, and energy efficient optimization. And we're also going to have benefits for the environmental friendliness, and we're going to reduce the carbon emission by approximately 20%. This is about safety and the economic benefits. And for the operation efficiency, so we're going to have reduce the cargo handling time, mooring time, and this, which also means that we're going to improve the rate of use of the ship itself. In recent years, the concept of smart shipping has drawn the attention of many international organizations like IMO, ISO, and other international organizations like the classification societies. The Maritime Safety Committee of the International Maritime Organization carried out a plan of maritime autonomous surface ships in 2018, so which is like about 4 years ago. The Working Group 10, under the supervision of Technical Committee 8 of ISO, also focused on the timely establishment of relevant standards on smart shipping in 2017. Because before that time, there were no standards. Then in the ship industry, we also know the ABAs, the DNV. They are like well-known classification societies. They also have released the classification rules, guidelines, and for smart ships. In China, we also have similar movements. The Ministry of Industry and Information Technology, Ministry of Transport, Defense Science and Industry Bureau, they altogether issued the development plan of intelligence ships, which is a plan for 3 years, and then Then after that, they published development guidance suggestions about the intelligent navigation, and then with all these plans, they want to promote the intelligent shipping development innovation center in 2025. Um, according to because different countries and different organizations, they may have different definitions of smart shipping. And I'm going to take the example of the China Classification Society, and which was released in 2020. So the framework of the smart ship covers 6 modules and 7 core advanced technologies. And the 7 main modules of smart ship are smart nautical navigation, smart hull, smart engine cabin management, smart energy efficiency management, smart cargo management, and smart integrated platform. So the first one is about, we know that there is this so-called the course optimization, for instance, and then the smart hull is the one that I will be talking about, and the smart engine cabin management. This actually has been been a topic in academia, and also has been applied in the industry for approximately 15 years already. And then smart cargo management and also the smart integrated platform are relatively new. The technologies used in smart ships include information perception. It's like how we're going to obtain the information. Then communication and navigation, and then energy efficiency control, trajectory planning, status monitoring and failure diagnosis, accident alarm and rescue, and autonomous navigation. So when it comes to smart hull, we're going to use, we will need the 4 technologies here as the items marked in red. So information perception, that is how we need to know the stresses, at least at some locations of the ship structure. And if possible, we would also like to know the sea state. And then after that, we need the communication and navigation technology, so that we can possibly optimize the course. Then we also have status monitoring and the failure diagnosis. Especially about the failure diagnosis, we need to know if there is a damage to the ship, or if there is a crack in the plate. Then we also have accident alarm and rescue. For accident alarm, we need to warn the crew that there is a failure and there is something wrong and in the ship structure. And then for rescue, here when it comes to smart hull, it means that the system is going to tell the crew that how are going to change, for instance, the speed, the heading, so as to reduce the stress response of the ship structure, and also possibly the crew may adjust the ballast water so as to reduce the stress response. Since we have several main technologies we're going to use in smart hull, but among those, the most important tool is the information perception and the status monitoring and the failure diagnostic technology. We know that to obtain the information about the ship itself, and also to find out the possible failure, or we need to find out, in addition to the hardware, like the sensors, the strain gauges, the sensors for acceleration, we also need to use other means to obtain enough information for us to make the decision for the analysis and also for the decision making. The failure diagnostic technologies include, for instance, we have sensors installed on the ship, but we know that no sensors are perfect, and the data we acquired from the sensors may have errors, and mostly actually they have errors. So how we're going to make sure that the discrepancies in this signal is caused by the structure itself instead of the sensors. Or how to make sure that the discrepancy of the signal in the signal comes from the drifting problem of the sensors instead of actual failure of the structure. And sometimes the signal representing the failure of the structure is of a small amplitude, but the background noise is very strong. So how do we find out or identify this weak signal to locate the structure failure? The smart hull is relatively, the concept of smart hull is relatively new, but the structure stress monitoring is not new actually. If I remember correctly, the first application of structure stress monitoring was in the 1990s, and as time goes on, because of the advances in the technologies of the sensors and also in the computer hardware to process, and the computer hardware is becoming better and better and fast enough to process the amount of data. The purpose of structure stress monitoring in the first place is to monitor the status, the stress of the structure in a real time, so as to avoid possible accidents. In the first picture, it is the ship MV Harbin cargo ship, and this ship broke up in Hades in the Black Sea, which was in 2020. If we had a system like a structure stress monitoring system installed on the ship, this accident could actually have been avoided. As we can see, the waves are propagating towards the ship. If we can change, if we find out the stress is very high, then we can change the heading. So if we change the heading, the wave load will become smaller, so that we can possibly we could possibly have avoided such an accident. The same thing with the two accidents shown in the other two figures, and so this is why we used this structure stress monitoring system in the first place. But now the structure stress monitoring systems, they are the they are the foundation of a smart house, because it is the only way we can find out how are the stresses in the structures, at least in the locations of our interest. The core idea of smart house is for instance, in the case of us or human, we have 5 senses. So we have we can see things, we can touch things, we can taste, we can hear, and we can smell. So our brain is like a computer. Our brain is going to process the information, all the information from the 5 senses, and then we're going to make a decision. When it comes to ships, similar, and the process is similar. So we have the sensors to measure the stress, to measure the acceleration, the temperature, the heading, the speed, and the waves. And there is all these the sources of information, and we develop a sophisticated system to process the information, and we can have a decision for the best choice strategy of operation. When it comes to smart home, it doesn't mean that we can. It doesn't mean that we can just simply use some like machine learning methods to achieve the objective. We also need to study the classic subjects of level architecture. For instance, we need to study the wave load calculation and analysis, because we need to calculate for instance, ocean-going ship. We need to calculate the waves acting on the ocean-going ships to find out the wavelet, and then we can use finite element analysis to find out the locations where we have high stresses, or we can find out the locations where we can capture the behavior of the ships, like smelling, sliming, springing, collision, this sort of responses. For the calculation of wave load, we have for the numeric methods, we have 2 methods. One is potential flow theory based, and the other one is safety based. For instance, the rest based methods. But because of the efficiency, rest based methods are not quite much used in the industry. So mostly in the industry, we still use, and also in the academia, we are using the potential flow theory based methods. And in the industry, they are officially released. There are 4 codes, and we know the BV Hydrostar, which is from the French Classification Society, sorry, the second one is DNV. Sorry, the text is wrong. So this is DNV. CSAM, and one of the modules is called VASIM, which it is used to calculate the wave loads. And there is also another one which is called WADAM, that is the calculation is done in the frequency domain. And then we also have VAMIT, which dates back to the code by Professor Newman from MIT. So the latest version is 7.4, and there is also this Compass Works suite for the calculation of wave loads released by the China Classification Society. And the sliming, because for most of the codes, the potential flow based codes, we use this energy method. So it is very difficult to find out the pressure acting on the flare of the hull. So we can use, in this case, we also use rest-based methods for the study of sliming node. This is important because sliming node is important because it is especially for ocean-going ships, like in the North Atlantic, the North Sea, in the Atlantic Ocean, where we have very large waves, and ships with big flares may experience sliming nodes. Then the other one is the direct calculation methods of hull stress. Basically, it is to calculate the stresses of the structure using wave load calculation codes, and also then with the finite element methods to obtain the stress distribution of the entire structure in different cases. In addition to the numeric methods, we also need to do the experimental study and also the tests at sea. There are two reasons. One reason is that in a towing tank, the waves are, first of all, there is a scale effect, and then the waves we produce we can produce in a towing tank are not actually the exact same as the waves we experience at sea. So for this reason, some researchers have been carrying out like very large model scales at sea, so as to eliminate the shortcomings of the tests in a towing tank. The first one was about 20 years ago, more than 20 years ago. The French Navy, they carried out a large mod test at sea for resistance and for the propulsion. And then this technique has been used for the investigation of performance of other performance like the wave loads and safekeeping, etc. So when it comes to this structure, we need to determine how much is the load acting on the structure. So for this, we need to know, we need to do hydrodynamics. So there are various topics in hydrodynamics, and we need different kinds of facilities. And the same thing with the structures. We also need to use the facilities, the right facility to do the investigation. Most of the structure stress monitoring system would consist the following modules or subsystems. So there must be a data collection subsystem, environment monitoring subsystem, and the FPGS monitoring subsystem, which is where we use this the fiber gradient sensors, and the data analysis subsystem. For instance, we need to find out the drifting, and we need, if there is, if there is a drifting problem, and then we should identify it. Otherwise, the data we receive is going, if there is drifting in the data we receive, and we would make erroneous decisions. And then the load calculation subsystem, strength assessment subsystem, safety forecasting subsystem, alarm and record subsystem, database systems, and also user interface. And it doesn't mean that a structure stress monitoring system must have all the modules, but it must have some of them. For instance, the data acquisition system, the data analysis subsystem. These are and also the warning and the record subsystems, and also the user interface. These are the most fundamental subsystems that we need to have in a structure stress monitoring system. So for an example for the structure stress monitoring system that we have been, I'm here in China. We have been using many ships. There is this data collection system that acquire the information of that inquires the information of the state and also the structure stress, and then we're going to process the information in the system. And this is the diagram of the gradient fiber optic sensors and the fiber demodulators. Basically, this sensors is different from the strain gauges that we use in a lab, because the one that we use in the lab is run on electricity, because there is electricity, so the signal can be distorted, and also because of it is run on electricity, we cannot use it in water tanks, and plus the reliability of those strain gauges is not very good. So the type of sensors that we have been using in our industry is now mostly optical. And for optical sensors, so the sensors itself, it is compressed, or it is either compressed or it is pulled together with the structure, so that it can, which means it can deform together with the structure, and then there is a mechanism inside the sensor, and then when it deforms, the wavelength of the light inside the sensor is going to change, and then on the other side, then there is this so-called the fiber demodulator, so it can read the change in the wavelengths, and then find out the deformation at the location where we have the sensors, and which means that we're going to have the strain, and then we can do the calculation. We can find out the stress. And this is an example of communication subsystem. So there is also like many elements. So we have the information we just have the information about the stresses, but sometimes we also need to have the information from other onboard systems. For instance, the waves, the speed. So we don't need to. We also need those information to make the analysis. Then, of course, we need to do the calculations. There might be a lot of calculations on board. Then there is also the data subsystem, and so we have like real-time wave data, the structured data, the failure probability, cumulative damage, and then the historic wave data, the statistics, information, etc. And the sensor data, I'm not going to talk too much about the sensor data acquisition system, because that is completely another subject. It's something that we use. Once we have we at least, I mean, as I have just I have mentioned earlier, that every structural stress management system must have the function of evaluation, so our assessment module, because we need to tell the crew whether it is dangerous at the moment. So here we have a table here. So this is one of the levels of alarm, depending on the stress.
So sorry, Xueqian. We have short times, please. 5 minutes.
Okay, I'm going to speed up. We have also have different the methods for evaluation. The one that is we have this reliability method based evaluation, and we also have we have this deterministic analysis evaluation, and we also have a reliability method for the evaluation, for the assessment. And this is for the fatigue stress strength evaluation, because we have the detailed information of the history of the stress. So we have we can use the methods. For instance, we have the methods to find out the cumulative damage to the structure. This is the application. I'm going to quickly go through this. So this is a very big ship. It's 400,000 dwt, ultra large ore carrier, and on this ship we did the optimization of the sensor distribution, which means we need to find the locations where we install the sensors, so as to find out the global response of the structure, of the hull structure. And then we also have developed the user interface, of course, behind which we have the algorithms over there to find out, to monitor the user stress, to the fatigue strength, to make the statistics, and also to monitor the motions of the ship. But there are also many challenges in this area. So, like how do identify the drifting problems, and how do we make the calibration, zero drifting, temperature drifting. So one of the possibilities that we test the sensors of the same batch in a lab. For instance, here we have a box where we test the error characteristics of the sensor from 20 degrees Celsius up to 60 degrees Celsius. And another one is challenge is the multi-source data fusion, the stress, temperature, acceleration, ship speed, sea wave parameters, loading conditions. So how we're going to find out the most useful, helpful information from all these sources. So this is also a challenge. And plus, the amount of data can be very large. And there was this the ships that we have just saw. We had about one terabyte for 3 months of operation. Then we also have a challenge that is data mining. So how do we identify the weak signals of abnormal structure behavior from strong like background noise resulted from the ship motion and also from other sources. For smart house, and because the smart house is a very new concept, but a smart house should consist at least one of the following elements: like digital twin models, data-driven model, or decision support system. For the digital twin model, here we have there are 2 examples. Here is like one digital twin model for wing, and as we can see, so when this the actual wing is turned and is pressed and released, and then we can see the response on the screen. So that which means that the stress distribution is reconstructed, and this is another one. So this is the digital twin, the whole digital twin models by DNV. So what they did is that they collected the stresses at particular points or locations of the hull, and then reconstructed the stress distribution of the hull of interest. Because, for instance, here in this case, we have the largest stress at midship, at least caused by the bending moment. So there are several methods for the reconstruction of the stress distributions. What we do is that the popular methods is that we we pre-calculate the stress distribution of the hull, and then we install sensors on particular locations, and then we find out the best match when the ship is operated at sea. We find the best matches from the database, and then we use the previously calculated stress distribution for the analysis afterwards, or for this decision making. For the data-driven models, and that is how to obtain the changes in ship structure itself, the plate thickness, cracks, damages, and also the environment and other exterior factors. And so for the structure, we know that a ship is operated as time goes, and then the thickness is going to change. There is going to be erosion, corrosion. So how do we find out these changes? And there also might be like local loads. Like for instance, this one is the ship that is operated in the polar areas. How to find out the load acting on the ship hull? So here what we do is that we use the so-called inverse calculation of moving ice load. Decision support systems. So for this one, because this is what we want most, so we need to predict the behavior in the next period of time based on the information acquired. And for this one, the method that we have been using in the industry is so-called short-term analysis based prediction of ship behavior. And for then we similar to the case of data-driven models, what we do is that we calculate the stress structure stress responsive ship at the range of heading, speeds, and sea states, and look for the optimal speed and heading at the present sea state. And also working to tell the captain that okay, you need to reduce the speed like by how many knots, and then you should change the heading by how many degrees, and then. Sometimes we also need to do this decision support together with maneuverability, with stability, because okay, if we change the heading, we'll change the heading. But the thing is that okay, the structure response is becoming lower, but the stability is a problem. So we need to make the decision considering many factors. Okay, in the when it comes to smart house, there are many challenges. For instance, nowadays almost all the house structures they are based on linear FE calculations. So non-linear FE calculations is still a challenge. Like accurate changes in structure itself, like the thickness, like reconstruction of the local stress distributions, because we cannot install a very big number of sensors on board. So how do we reconstruct the local stress distributions, and the prediction of sea waves and the motion stress response of the hull in the next period of time, and the prediction of complex structure behaviors, the evolution of crack propagation, corrosion, and damage, and also the structure safety, maneuvering, and the stability integrated operation decision in waves. And there are much more than this because it's still being studied, and also I should not elaborate too much on this because of the time reason. Thank you very much.
Thank you, Dr. Xueqian Zhou. We have any questions? So I have any questions here. I know that you put many challenges, but in your opinion, which is the most difficult to make the most intelligent or autonomous the ship more intelligent since the point of view of a smart hull?
This is a very difficult question because there are many challenges actually. Well, for me, I think that the most difficult one is to, as of now, is to reconstruct the stress distribution of the hull structure from a limited number of strain gauges. This is still very difficult. Because the ships, a ship is a three-dimensional structure. It's very different from the bridges, from the train rails. They're one-dimensional like structures. It's very for them. It is easy to find out the cracks because the vibration modes might be different. The frequency might be different, but in our case, it's very difficult. The structure itself is very difficult. This is one challenge. Another challenge is to predict the behavior in the next period of time. This is still very, very, very challenging. Yeah,
that's right. That's right. Thank you so much for your presentation.
I have one question.
Oh, okay, Jose, can you ask, please?
Yes.
You know, we used to develop analytical formulations to understand many kind of phenomena.
Okay.
No, yeah, it can be hydrodynamics. It can be structures. You know, whoever you are using some kind of mathematical model to have your virtual ship and somehow in this virtual ship predict any kind of accelerations or danger to the ship. So it seems to me that analytical formulation, simple mathematical formulation, are now important, are more important, because finite element formulation of CFD formulation, it's almost impossible in this kind of cases. What is your opinion?
Well, well, thank you very much, Professor Jose. And I'm going to make this short. And the traditional methods are still very, very useful and crucial when it comes to smart hull. That is the foundation of what we have, what we're doing right now about the smart hull. You just mentioned that the simple methods, they're very useful. They're even more useful, like the empirical ones, they're even more useful than the sophisticated methods. For instance, even like the simple methods, like the empirical methods, they're even like the beam theory. Sometimes they're more useful because they're convenient. They're even more useful than the FE and the finite element analysis, more useful than the potential theory, flow theory based or RAS based methods. But however, now in the industry, there are two trends. One is that environment issue, so that is green ship. So because of this carbon dioxide emission problem, DNV has launched their initiative of energy transition and looking forward towards 2050. So that is a very big move of theirs. Another one, that is the smart technologies, because for some reasons, they traditionally, and what we do, the process is like this: we design the ship, and in the methods, like almost everything is designed, is calculated, is under control. But once the ship starts to be constructed, your control about the reliability, about the efficiency, about the status of the ship is very limited. What we have, the approaches, there are two approaches. One is that we have regular inspections. This is one. The other one is that if there is a failure that or damage, we repair. So, but that it doesn't mean that we have the best operation strategies for the ship. It's not for the best economy. It's not the best for the safety. It's not the best for the efficiency. Since now there is this technology. If this technology is ready, we can possibly, for instance, there was this cruise ship that company, they contacted us like a month ago. What they want is that, okay, we want to reduce the frequency of regular inspection just for one time, like in a couple of years. And that would be a lot of money for them. So that is their consideration. And for us, the problem is we'll find the right methods to realize the smart hull structures. I don't know if I have answered your questions, Professor.
It's fully clear. I'm happy for the answer. And in somehow we find the way to reduce dramatically the computational time by using artificial intelligence. For example, we train some neural networks to mimic what finite elements can do based on analytical formulations.
Yeah. Yes, Professor.
This could be a really good.
Yeah, but the thing is that with machine learning based methods, how are you going to find the right samples, the training sets? This is a challenge because we cannot. Yeah, this is very difficult.